excited to be here and give my talk on a bag of freebies from competitive machine learning. Before we start, a few words about me. So I'm doing computer vision for probably 8 years from now, and I switched recently to machine learning, which I've been doing maybe 2 years from now. And what I found works best for me is to learn by solving challenges that are available online on the platforms like a Kaggle or the Top Coder. So learning by solving real problems is really what works for me. So I'm here to share what are the most used tips and tricks that you may basically use in your work, in your product, and benefit from them. So when we speak about competitive machine learning, we usually mean that there is some task, that there is some data that is available to you, which is labeled, and there is some metric that is basically a goal, and your goal is to optimize this metric. So given that, you need to build a model that performs best and best among the other competitor solutions. So one can list probably the most well-known platform like Kaggle. There are also Top Coder site and the Driven Data, and also Japanese platform like Signate, where one can find plenty of different competitions of any kind. It can be image classification, segmentation, object detection, time series predictions, all of the kind, and one can find a solution to its related to its work. So most of the time when we think about what is the machine learning and what are the solutions, we often think like we just stack XGBoost or add more layers to our network, making really heavy solutions, crazy ensembles of 20 models, and this is how we win. Most of the time it's not. The common trend right now is to limit the capability regarding computing power, the inference time on the competition, so that everyone is in the same position regarding how much computing power they have to make their predictions. So that's why stack more layers is not work anymore. And one should find a more sophisticated way to increase their score. Therefore, we will talk about a few tricks that group it into the loss function tricks, tricks related to data sets, and the tricks related to learning, training of your model. So just a brief example of what are typical challenges that are available on a Kaggle from just the past half a year. For instance, a fine-grained segmentation of an image to segment out items where on the person. So this is really challenging because it requires you to not only segment, let's say, high-level apparel, but let's say you need to segment also fine details like a zipper or some necklace, something. So there is a huge variation of what the objects to be detected. Another interesting challenge is to predict the interaction between atoms in a molecule. So this is really into the physics of the atom tasks, and I suppose there are no one in this room who is actually doing physics of atom, right? But probably some of you work on the graph data. And the point is, you can learn from that competition, from the solutions from that competition, what was the tips, what was the solutions that people used, what was the model architectures or general approaches that work on the graph data that you can use later on. And this is a great value in the competition, so that you can learn from others, what others did, what worked, what did not work. And this is also very important. For instance, one can learn how to detect the proteins on the image, which is a multi-label classification, and is also really challenging because based on this image, one can say there are 5 types of protein, right? But it requires a domain knowledge. But if your problem demands multi-label classification where there is a long tail distribution, you still can learn from it. Or some object detection puzzles where you should translate old Japanese characters into contemporary alphabet. So everyone can find the solution that somehow reflects to his own tasks. So the first section we are going to start is the loss function tricks. So in many problems, it's crucial to choose the correct loss function. And the correct here means that in ideal case, it should correlate with our target metric. Most of the time, it's not, because let's say it's impossible to directly optimize F-score. So one should find some proper proxy loss function that correlates with the target metric. And for the classification problems where there is a huge class imbalance between the positive and negative samples, it's known that binary cross entropy is probably not a very good solution because it's really sensible to the distribution of the classes, and on such a huge class imbalance, it doesn't perform well. So basically, if we have class imbalance 1 to, let's say, 10,000 samples, then our easy samples will just dominate in the loss. For example, in this case, we have 40 times bigger loss from the easy samples than from the hard samples. And in this case, basically, the model cannot learn anything and cannot converge. So this was a problem that authors of the RetinaNet faced. And RetinaNet is a single-stage object detection that reached a state-of-the-art performance in 2018. And the key for this was a use of the special loss function called focal loss, which is extension to binary cross-entropy function, which adds a small penalty term to penalize easy examples. So they contribute much less to the final loss, to the sum of the loss. So here you can see 2 plots. So the blue one is the focal loss, and you can see that it decreases much faster towards the 0 than the red one. The red one is the classical cross entropy. So what basically it means? It means that if your problem assumes a huge class imbalance, that you can change your binary cross entropy to the focal loss and give immediate increase if in the convergence speed or in the accuracy. And this has been proved by past Kaggle competitions. Especially it works quite well in the image segmentation, in the classification problems, where you have really rare support for your, let's say, true samples. For instance, there was a competition on segmenting X-ray images to detect pneumothorax disease, where the actually positive number of pixels were really low, maybe 100 or 200 pixels out of the 1,000 pixel image. And in this case, focal loss helped to model to converge much better than the classical cross entropy. So next improvement to the focal loss is the reduced focal loss. It's not very well known loss function, but essentially it's helped guys to win the XView object detection challenge. And as a result, they wrote a paper where they described this approach. So reduced focal loss aims to solve the low recall for the rare classes problem. And it works like the classical focal loss, but instead it first, it doesn't introduce any penalty for the loss. The red one is the reduced focal loss. And after the model begins to predict good enough results, it drops with really, really high speed.
So, and essentially this has a meaning that if the model is already predicting well enough, then we just quickly drop the loss to the zero so the model can concentrate on something else. And essentially, it increased the recall in that competition by 11%, and guys won this with a great margin from the others. So this has really helped also. So next loss function is really popular among the segmentation challenges is loss function that's soft dice or a soft Jaccard. There are just really similar ones. And here is an idea. Usually when we are doing any kind of segmentation problem, we are interested in the quality of the segmentation. And the quality measured in the how good the predicted mask overlaps with our predictions. And the point how to measure it is to use or dice or Jaccard metrics with an intersection over union. So how do we optimize that directly? So essentially, there is no way to optimize it directly, and most of the time, we are using either cross-entropy or the binary cross-entropy and just classifying each pixel individually. But it turns out that there is a way to fake this dice by computing so-called soft dice or soft Jaccard metrics, which allows to optimize this intersection directly. And it's really simple to compute, so we basically multiply element-wise our mask with our predictions, and this gives our intersection. We sum them, this gives our union. And that's it. We divide and we get the loss. So, and this simple idea helped to win the Carvana Image Masking Challenge competition, where it has been first announced as a loss function. So what it gives us, it makes the predictions more sharp on the edge, where typically the model introduced the most error. So it stimulates model to give more confident predictions on the edge, so they looks sharper, and it's easier for us later on to make them a binary. Okay, yeah, this is a list of the competitions that were either winning solution or a second place solution that used this trick. This is what we know that has been reported that guys were using it, but I assume that maybe the list can be longer. So next loss function is wing loss, which is used for the regression problems. So typically when we are doing regression, we use either mean square error or maximum absolute error losses as our default ones. But the problem with mean square error is that it's really sensitive to the outliers in our training data. And this has negative impact on our model accuracy. So to work around this, it's been proposed to use a wing loss function which has a different shape than the MSE. And essentially what it does, it's really similar to the idea in focal loss. So once we get closer to the optimal, once the residual gets less than some threshold, the loss drops down greatly. Otherwise, it's just L1 loss. So this helps to reach a state-of-the-art result on the facial landmark localization. And also, it helped to take a gold medal in the blindness image classification, where it's been also a regression problem. So last trick here is you are not bound to use only one loss function. It's a common practice to combine losses, multiple, with different weights. They are found experimentally, but the idea here is by combining multiple losses, you can change the loss landscape of your model, and therefore avoid stacking in some local minima or help model to concentrate on different aspects of your problem. Suppose it's very common to combine cross-entropy with a soft dice loss, or use a focal loss plus lavage loss, or figure out any other combinations that you can think of. It's proven to work constantly on Carvana masking challenge, on the data science ball, on salt identification, and we see constant top performing teams using these tricks, and it really helps. So next section is the data set tricks. So what we can do with our data basically to give a boost. So first thing that comes to our mind when we are working with image data is image augmentation that Yuri already mentioned today. So I cannot say how important it is. I cannot overestimate the importance of the image augmentation data. It's basically a free way to extend your data set, increase its variability, and prevent your model from overfitting, especially when you have a lot of small amount of data. Image augmentation can help you to make much larger data sets by randomly applying transformations that keep semantic meaning of the image, but change its pixel distribution. So to say, you can make image sharper, brighter, you can decolor it, you can change colors at all, you can shift the channels, you can apply some affine transformation or elastic transformation. There are plenty of ways to play with image augmentations. And it's all help to prevent overfitting and increase accuracy of your model. So here is just not a full list of the competitions that reported that image augmentation has been used. And in particular, the augmentations library that I contributed to has been used. So I don't see any image competition that's currently happening that not using it in the top performing solutions. So all of them using it, and I encourage you to also give it a try if you are not using it already. So next idea that's also relevant to image augmentation is so-called test time augmentation. So idea is simple. Once we have a trained model and we have an image that we need to make predictions to, why we should send only one image? Let's flip it. Let's make it brighter. Let's resize it. And then let's average predictions for all of them and see what happens. And what happens is the model variance is reduced. And the more images, the more augmented images we send in, the more variance is reduced. And this improves a score a lot. So this is commonly used tricks and also in many competitions since it's a free lunch, basically. You don't need to retrain your model. You don't need to do any with your data set. You just predict n times instead of one, average them, and voila, you get a great boost on your model. So it's really simple. You just average the probabilities, and that's it. So next thing that I wanted to talk about data, and probably this will be also covered in the next talk by Dmitry, is the adversarial validation. What it is, the problem that it tries to solve is a different data distribution in the train and the test sets. So this means that, let's say, in our train, we have more apples than oranges, and in the test set, it's vice versa. So our model can be biased to it, and how we can basically avoid it. So the idea here is to build a classifier to predict whether a particular sample from the train set belongs to the train set or it's more like test one. Right? While training this classifier, then we do predictions for whole train set. So we kind of classify what train samples are more looking like the test ones. So an idea here is that we validate on the test samples that more looking as a test ones. So what it essentially does, it gives us the validation set that is more in terms of the distribution close to our test set so that we can evaluate our model with a higher predictability. Next trick that I'm going to talk about is label smoothing. So it's quite often that our data set has errors, labeling errors or some bugs during labeling or any sort of errors that can confuse our model. So even in the Kaggle, where the data are known to be more or less clear, it's still the case. So to facilitate this issue, a label smoothing technique is proposed. So what it basically does, if we say we are solving classification problem, instead of assigning labels of 0 and 1 to our targets, let's introduce some epsilon, which is like 1, -4, -5. And instead of 0 and 1, we just do epsilon and 1 minus epsilon. And we use same cross-entropy function. In this case, in our misclassified, mislabeled example, the loss will be much lower. And this will have the following impact on the model. Model will not be making overconfident predictions. And by discouraging model to make these overconfident predictions, we reduce the impact of the wrongly annotated labels to the final accuracy. So basically, the bottom line is model becomes less sensible to annotation errors, and therefore we dampen their impact on the accuracy. So next step is the pseudo-labeling. It also correlates with the active learning that you just heard, and it's more specific to the Kaggle competitions, since it's not allowed to do manual annotations of the test data. So therefore, to not violate the rules, one can do pseudo-labeling, which is essentially a process of iteratively increase the model by first making predictions on the test set, choosing only the confident predictions based either on the entropy or uncertainty factors, and adding them to the training set. Then we retrain the model. We again repeat the round once again. Again, we pick the confident predictions, and we repeat this process as many times as we need. And the idea here is that every time our model gets more and more accurate, it's learned more and more from the test, and clearly we should validate on some holdout data to avoid we are not overfitting or we are not introducing any bias. But essentially, this trick also helps when we are not enough of our data or there are many data in the test set that we want to use somehow. This solution is also helping, for instance, winners of the salt identification challenge use this trick to basically secure the first place. And here, this is an image exactly from their presentation. So this is really also helpful for the getting more from your data. So last but not least is the training tricks. So suppose we know what to do with our data, we end up with our model architecture, and what we can do with the training to squeeze every single % out of model. So first thing that comes out is so-called multitask learning. Here is an idea that let's ask our model to make auxiliary predictions or solve other tasks that correlate somehow with our main task. One example here can be, let's say we are doing image segmentation problem of detecting, let's say, disease on the image, right? Why not we make a second head to the model to predict also is there any disease at all or not? It could be a binary classifier that will just predict there is a disease or there is no disease. So we then can use this output to post-process the mask that has been predicted. So if the classifier says there is no disease at all, we disregard the mask predictions at all. So this post-processing first helps to prevent any spurious artifacts on the mask to appear in your submission. Most of the time, the target metrics really heavy penalize for these false positive predictions. And also what it helps to model to generalize better. And one can figure out many other ways to use this multitask learning. For instance, we can also ask model to classify image plus do a reconstruction of it. So this also forces model to learn how to encode the image representation in a smaller shape to concentrate on the details that we are interested in. So multitask learning helps model to generalize better and concentrate on the different aspects of the problem. Can you do full screen? Okay. Thank you. Okay, next trick is cyclic annealing of the training. So what's the story about this trick? It's well known that stochastic gradient descent tends to produce a better generalization than Adam optimizer, but at the same time, Adam is known to be much faster regarding convergence speed. So the simple idea here is that we start training with Adam optimizer, and at some point we switch to SGD, which kind of polish our weights because it has different step directions. And then we repeat this process a couple of times with a lowering learning rate. So by switching optimizers iteratively, we therefore kind of moving in a different direction. It's like a different drivers that drives the same car. They do it differently, right? And here we introduce some diversity, and essentially it also helps model to converge faster and to the better minima. I couldn't find any references to this, but from the past competitions, I heard this trick, and I can say that, yeah, it really works well. So next thing is gradient accumulation. So typically when we are training our network, we are doing forward pass, when we doing backward pass, where we update our gradients. But actually it's not obligated, we are not obligated to do this every step. We can do, let's say, 100 of batches of forward pass accumulating gradients, and then we do backward pass. So why actually we want to do this? And here the answer is by averaging these accumulated gradients, we essentially fake our batch size to be n times larger. Suppose our GPU can handle batch size of 128. By doing gradient accumulation of 100 of batches, we fake our batch size to be 1,280. And it's well known that the SGD works better with a larger batch size. And this trick helps here to, on a fine-tuning step of your model, to squeeze this half of the percent, let's say, out of it for free. Another problem that this trick solves is the small batch size. Suppose you're training a really heavy model and your batch normalization doesn't work, right? In gradient accumulation, you can accumulate the statistics and allow it to train with the batch norm. That's it. So last but not least is a trick that becomes more and more popular with the help of the NVIDIA mixed precision training framework, which allows us to train our models with a floating point of 16 bits instead of 32. So this has immediate result of decreasing the amount of memory that is required to train your neural network model twice. And essentially, it keeps the training accuracy, training stability on the same level. And this allows you to basically feed 2 more times data than before. And this is also crucial for the challenges where your models are really heavy, or you're doing image segmentation, which is typically demands much more GPU memory than, say, classification problems. In this case, training with a mixed precision is really key to success. And on the latest generation of the NVIDIA chips, it also brings the performance boost, since the tensor cores can do FP16 calculations 2 times faster. So not only you get 2 times more space, but your calculations essentially gets faster, which is also cool, right? So this trick is becoming more and more popular on a Kaggle, and unless you're not using some really unstable model, it works just out of the box. So next trick that I'm going to talk about is metric learning. Metric learning is a technique that enforces a latent space of your model to have a property of some Euclidean space or any other space that defines it, so-called metric, that allows you to compute how similar images are or how dissimilar they are. And the typical problems that can be solved with this, like, is a person identification, or like in this example, identification of the whale species by photo of its tail. So the problem that this represents was also a Kaggle competition where one should identify the whale's exact species by a photo of the tail, and among the roughly 1,000 of the examples that were labeled, there were really very big amount of the whales that were not new whales, not classified, not known at this point. So with a metric learning approach, it's possible to not only classify this is a whale A, this is a whale B, but also to say this is an unknown whale and we don't know who is this. So there are plenty of options to do this metric learning. Most classical and well-known ones are the contrastive loss or the triplet loss. Less famous are central loss, cosinus phase, and two latest, the arc phase is really a new one, maybe from 2018. Which tries to represent this latent space as a circle, and direction of where it's pointing is basically this embedding space represents. So, and the last divide and conquer method was used exactly in the whale competition, and it then been made as a CVPR paper and approved on this. So I really encourage you to take a look on it. It looks really promising. And it's been used in the Google Landmark Retrieval Challenges, Human Protein Atlas Classification Challenge, and also in the Whale Identification Challenge. That's all from me. Thank you very much.
And we have a few questions for you, okay? Question number 1. One second. Loading.
Okay, yeah, I will read the question. What should you do if in a regression task there are outliers in train and test both? So if there are outliers in the train set, then we want to use a function that is robust to those outliers. It can be smooth L1 or a Cauchy, or the mentioned before wing loss function that are much less prone to, much less sensitive to the outliers than, let's say, mean square error. So that's one part of the answer. Choose the loss function that's less sensitive. Second, you still can do negative mining and see where your model makes wrong predictions on the training set, so that you still can do some data cleanup. No one said you shouldn't do it, right? Data cleanup and the error analysis is also very important in any data science work. And cleaning data usually gives much better boost than any model tricks or playing with the activation functions or model initialization, something like that. Cleaning data is the cheapest and the most efficient way to increase the model accuracy. And if they're in the test set, well, you cannot do much with it, right? Since it's a test set and you don't have a control of it. That's it. Next question?
Next question, yes.
Which of these tricks did you use in a blindness detection challenge? Not a private sharing. Well, the competition has already ended, so it's okay. In the blindness detection challenge, I used the win gloss, since the problem initially was stated as the classification. To whom not familiar with the challenge was to diagnose the stage of the diabetic retinopathy in the eye by taking the eye image. There was a 5-class classification, as it initially stated, but then it's become clear to me that it's better to solve this problem as a regression problem, since that decision boundary between, let's say, stage 1 and stage 2, or stage 2 and stage 3 is not very clear. And different doctors assign those classes really differently. So instead of classification problem, I solved this as a regression problem. And it also became clear that the data set also contains noise. So I used the win gloss function to avoid these labeling errors. And it's essentially helped me to reach the 7th in the overall leaderboard in this challenge. I would say this was the main. And also I used image augmentation, which was a really heavy one, and the test time augmentation as well. If you are part of the open data science community, you can write to Artur Kuzin. He has a lot of GPUs on his kitchen. And he can maybe give you some. But right now, yeah, Kaggle is reducing the amount of GPU, amount of the computer resources it has to really limited amount of GPU hours, maybe something like 30 hours per month, which is really nothing. So you can still use Google Colab, which gives you Tesla K80, which can run for maybe 8 or 9 hours in a row, which is more than enough usually to train some decent model, or at least to run some experiments. So you are not bound to use Kaggle resources only. Still, there are plenty of ways. And in many competitions, like in the recursion cellular competition that is happening right now, they were giving resources for Google Cloud for their TPU that one can use for solving this challenge. So it's also, so there are ways. And you always can buy some used GPU on eBay. So averaging test time augmentation predictions is not the only option. So there are a couple of ways to average them, right? So one can do geometric averaging instead of just computing a mean or a harmonic mean. But what from my perspective, from my experience in the segmentation challenges, simple averaging performs the best. So in the blindness detection, I tried reduced mean or median to average them, and for me, simple averaging worked the best. I disagree, because Data Science Ball 2017, I believe, was on the plankton classification. I may be wrong, but that's what I recall. It's good. But the long answer is from my experiments and experience, it works at least as well as classical Adam. And I've been using it for the blindness, and currently it's my default one.
And last one.
Okay. It is, and this is a goal. So our leaderboard position is evaluated on the test set that we have access to. So the competition goal is to have this highest score on the test set. So that's why we want to optimize for it. Yeah. Clearly, it's tricky to understand at which point we are really optimizing and introducing a bias for the test set. That's why we need to keep some holdout data set to ensure we are not doing worse. And still, when we are doing pseudo-labeling, we add our pseudo-labeled samples to the train set that is still remain unchanged, so that with this we kind of keep our model and trying to sit on the both chairs, so to say. And also it's a good idea to, in case we are using pseudo-labeling, also use a label smoothing together, so that instead of computing the cross entropy, essentially our loss functions becomes a Kullback-Leibniz divergence, which is basically better and less sensitive to the outliers, even if we do some wrong pseudo-labeling.
Many thanks for Evgeny.
Thank you.